In this chapter, we will be looking at quadratic equations. In this lesson, we're going to look at factoring, greatest common factoring, difference of squares, and grouping. And we'll start with greatest common factoring.
All right, hi everybody. So in this lesson we're going to take a look at factoring, and we're going to look at different types of factoring. You can see we're going to take a look at greatest common factoring, difference of squares, factoring, and grouping. And we're going to start with greatest common factoring. And before we get too deep into this, I want to make sure that you understand what I mean when I talk about factoring. So for example, if we've got the number 98 here, and I want you to identify the factors of 98, okay? You might not know right off the top of your head what the factors of 98 are, but you can probably guess that 2 is one of the factors. Now, the word factor refers to the numbers or the expressions that are being multiplied together to create another one here. So now, when I want to figure out what the factors of 98 are, I recognize that probably 2 multiplied by something is equal to 98, because that's an even number. In order for me to figure out what the other factor is, what I need to do, and it's important that you catch this operation here, I actually need to take 98 and divide it by 2. And when I do that, I get, oh my gosh, it's going to be 49. So by identifying a factor and dividing it out, I figure out what the other factor is. But to write it in factored form, I need to write these two multiplied together. I know that seems kind of weird. There's this kind of interesting interplay between multiplication and division here. But once you find one factor, okay, you divide this out to find the other factor. But when you write them out, you write them as multiplied together. And you can go one step further here with this. You probably already know that 49 is 7 times 7. And so I can write 49 expressed in terms of its factors as 7 times 7. And so by using division, okay, I can figure out what the different factors are. And when I write it in factored form, what I want is I want them all multiplied together to equal the original expression here. Now, we're going to take a look at this in a little bit more complicated of a way here because we're going to introduce variables and whatnot into this. Anyway, and so let's talk about common factoring here. So if there's a number that divides into each coefficient, remove it by dividing each coefficient by that number. So again, we're talking about that division there. We divide it out to see what it is that we're looking at, but then we write it as they're being multiplied together. Okay, fractions should be removed. That's a really important point. And if the leading coefficient is negative, then usually we're going to take out a -1. Okay, that's good advice there. If there's a negative in front here, just factor it out. These forms are pretty. Okay, and I think I can use that word correctly here. They look better if that negative has been factored out. Now, we want to check and see if there are any common variables to each term, values that are shared by each term, and then we're going to take those out. Because essentially what common factoring is, oh, and then finally, if there's a binomial common factor, we're going to remove that too. Essentially what common factoring is this. Let's say that I've got 3 multiplied by a plus b. Okay. I know that in order to multiply this out, the 3 has to get distributed to both of those terms. And so this becomes 3 multiplied by a plus 3 multiplied by b. Okay? So I distributed the 3 to both of those terms. Now, what I'm asking you to do in the act of factoring is to actually take this expression and go back to this one. In other words, I'm going to look at this. This is what I'm given. I want you to recognize, hey, I see 3 in both of those. Just like up here, I saw that there was a 2 in that 98. I see that there's a 3 in both of these. And so what I want you to do here is I want you to write that 3 down, and that's going to be multiplied by, well, what? What did I multiply 3 by to get this here? Well, to do that, I'm going to divide both of these terms by 3. If you take 3a and divide it by 3, I'm left with an a. 3b divided by 3, I'm going to be left with a b here. And addition, okay, I'm adding those two because there was addition here between those two terms. So 3 multiplied by a plus b. And I write it as a product. Okay, these two things multiplied together, these are the factors. Their overall result when you multiply them together is their product right here. So in essence, common factoring is the process of going backwards from the product to the original factors that were used to get it. Anyway, I know that's a little bit of theory here. It'd probably make way more sense when we start to actually do some questions. Okay, so let's take a look at some examples here. Now, I'm going to do these first few. I'm going to throw in some extra steps in here just to make the point about how common factoring works. I'm hoping that soon you won't need to do stuff like this. So right now, 3x minus 9, I'm going to break up 9 into its factors. And I know that 9 is 3 times 3. And so now what I see here is that each of these terms here has a factor of 3. So that 3 was distributed through. I'm going to take and write that out front. And it's going to be multiplied by, well, what? Well, I got to divide. I'm going to take that term and divide it by 3. 3's will cancel, leave me with x. I'm going to take this term right here, divided by 3. Now there is a subtraction in between. So we subtract, and there is a 3 left over. So how do I know I did this correctly? If you distribute this 3 back through, it should take you right back to the original expression, and in this case, in fact, it does. So 3 multiplied by x minus 3, these are the two factors of 3x minus 9. All right, this one right here, I have got 10 is the same as 2 multiplied by 5 multiplied by x squared multiplied by y, plus 3 multiplied by 5 multiplied by x squared multiplied by y. Okay, so what has been distributed to each of these two terms here? Well, clearly in terms of the numeric coefficient, there's a 5 there. Okay, some 5 has been distributed to both of those. But I can do a little bit better than that because notice that there's an x squared in both of those. There's also a y in both of those. Okay, so what has that been multiplied by? Well, when I divide this out, when I divide that first term by the 5, the x squared, and the y, I'm only left with the 2. And when I divide this term here by the 5, the x squared, and the y, I'm only left with a 3. Now it turns out in this particular case here, just have a quick look at this. It turns out that, hey, 2 plus 3 is 5. And when you multiply that by this term, you're going to get 25x squared y. Now, that is, in fact, identical to what you would do if you just added those together. Notice the variable portions of those two terms are the same, so all I would do is add the leading coefficients, and you'd get 25x squared y regardless. Whoops, sorry. But that's an interesting question because it's neat to see that actually those, I can come up with the same result, either just by adding them, which is the easier way to do this, but the factoring maintains that as a result. So I can come at that answer in a couple of different ways. Let's take a look at this one. Now, normally what I would do is I would break that 4 apart. Well, we might as well do it. This is 2 times a squared times b plus 2 times b cubed times a plus a. Now, what I'm looking for is something that's common to all three of these terms here. I see a factor of 2 here and a couple of factors of 2 here, but there's nothing here. I see a factor of a squared here. There's an a here and an a here. Okay, so the a has been distributed. But even the b, I can't do much with the b because the b isn't common to that last term. I'm looking for something that I see in all three of those terms here. Now, when I divide this first term out by a, okay, there are 2 factors of a there. I can see that because of the a squared. That's a times a. Now remember, when I go to write it in factored form, I have to use division to do that. 2a squared b divided by a is going to be 2ab. 2 times b cubed times a, okay, is going to end up being 4b cubed. And then when I divide out that a, I don't need to write that anymore. A divided by A is going to be 1 here. And I actually say that on purpose because when I divide out that A right there, remember, because this is division, when I divide A by A, this A that I'm taking out, remember that I'm going to be left with 1. Really, really frequent mistake that people make here is when they divide that out, when they do the factoring, and they cancel out, they actually leave it. They make it go away and treat it as if it's a 0. Please remember that A divided by A is actually going to equal 1. Let's take a look at this one. And so once again, what I'm going to do is I'm going to write out the factors, the numeric factors here. 25 is divisible by 5. Okay, it's 2 factors of 5, x squared. And 75 is really just 3 times that. So it's 3 times 5 times 5. And there's an x there. Now again, I'm hoping that after a while you start to see these patterns and you don't need to do what I'm doing here. There are 5s distributed to both those. In fact, there's 2 5s distributed to both of those terms. Additionally, there are 2 factors of x here and there's a single factor of x here. Because remember, that x squared means x times x. So there's an x times x here and then a single x here. So I can take out an x. When I divide now this term by this, 5's cancel and one of the x's cancels and I'm left with just a single x left over here. When I divide out the 2 5's and the x from this term, I am left with a 3 there. And now when I multiply these guys together up front, I get 25x x plus 3. And it would be awesome if the more comfortably that you get with this, the quicker you can jump to that. In fact, I suspect a lot of you will be able to jump right to the answer there without doing any of the in-between stuff. Now, there's no difference here when there's a binomial factor. Absolutely no difference. Because the truth is, this is an unknown, just like y is an unknown. So let me put it to you like this. You might, if the binomial there confuses you, you might even think of it like this. Do you know what y is? Well, no, I haven't got any idea what y is. So do you know what y minus 3 is? Well, no. So I tell you what, let's just call it a. So we'll call both of those a here. And now I can see that the value of a has been distributed to both of those terms, and I can divide that out. So I take the a out, and I'm going to be left with 10x from the first term and a 7 in the second term. Now, that's how that works there. It's just that there was no a in the original expression. Instead, that was going to be y minus 3. So I'm just going to have to put that y minus 3 back in. And it was multiplied by 10x plus 7. Now, I want to take a look at this one over here. This is a very similar sort of a problem, but notice that the binomial factors here, they're not the same. But you know what? I can get around that. This one right here doesn't look really pretty to me. I don't like that. I don't like the fact that the 5 is in front of the x here. So what I'm going to do is I'm going to make this look pretty first, and then I'll deal with the factoring. So first of all, what I'm going to do is I'm going to reinterpret this subtraction as adding a negative. Now, what I gain by doing that is order doesn't matter for addition. Order matters for subtraction, but order doesn't matter for addition. But the nice thing is I can interpret that subtraction as an addition if I just interpret it as adding a negative. And now I can switch the order of those two. Now that's pretty good, except that this x here is positive, this y is negative, and here this x is negative, this y is positive. So just like we said earlier in the lesson here, if we've got a negative in front of the expression here, we want to factor that out. So what I'm going to do now is I'm going to take a negative out of this term right here. Now what that's going to do is change the signs here. So I've still got this subtract 4, but now I'm going to have this negative 1 that I've factored out of that, and that's going to change the two signs in here. It's going to make that positive x minus 5. This is going to be minus, now I should say it like this, order doesn't really matter when you start to multiply here, so what you end up with here, okay, that negative right there can turn that negative into an addition. It's like subtracting a negative here. So that'll become 4, adding 4 times x minus 5. And now that x minus 5 factor is common to both of those terms. And again, this is like having, I don't know, the big old A. If you don't like looking at the binomial factors, just think of this as one big old letter A. This is a big old letter A. I factor the A out, and in that first term, I've got this X I'm now left over with. In the second term, I've got that 4 that I'm left over with. So if you multiply this through, if you multiply A times X, you get this bit right here. A times 4, you get this bit right here. And it's only now at the end that I then go back and admit that wasn't an A, that was an X minus 5 multiplied by that X plus 4. Okay. And that's how I would deal with common factoring when we're working with a binomial factor.
Now we'll look at difference of squares factoring.
Okay, now we're going to take a look at difference of squares factoring. And the way we kind of come across this here is, notice that if you take A plus B and multiply that by A minus B, okay, when you expand that out, you're going to get A squared minus AB, okay, plus AB minus B squared, okay? And then your middle terms here are going to be the same term, just with opposite signs, so they're going to go away. So what you're going to be left with here is A squared minus B squared. So that's what happens when you expand this out, when you multiply those together. And notice the relationship between those two. It's basically the same binomial, it's just the middle sign is different. We have an addition here and a subtraction here. We call those, okay, when they look like that, we call these binomial conjugates. Okay? We call those binomial conjugates. And we notice that when you multiply those together, you're left with just the square of the first term minus the square of the second term. Now, what that means for me, though, is that let's say we ignore all this. What if I'm presented with a problem that looks like this? That's A squared minus B squared, a squared term minus another squared term. Well, I know, based on my experience going forward, that this should be the same as A minus B multiplied by A plus B. I should be able to go backwards and create the binomial conjugates based off of this. It's just going to be the square root of the first term minus the square root of the second term multiplied by the square root of the first term plus the square root of the second term. That's all I'm doing, okay? So it's only a difference of squares right here if it contains the two terms that are both perfect squares and it's a subtraction in between. And then always remember to take out the greatest common factor if you can, okay? Now, let's have a look at some examples. Okay, let's have a look at some examples. So here, notice in this one that we've got two terms here. They're not perfect squares, each of them here, but there is a common factor of x there. So I can take out the x that has been distributed to those two terms. And when I do that, remember to write what I'm left with here, I have to do division. X cubed divided by that x is going to be x squared. That negative x divided by that x is going to be minus 1. Oh, and now what I'm left with, though, this x squared minus 1, well, that is a square minus a square. So I can break this apart into its binomial conjugates, x minus 1 multiplied by x plus 1. And there we go. Now I've fully factored that. Okay? So it had a common factor and a difference of squares there. Okay, let's take a look at another one. Now in this case right here, right away I see, first of all, that this is a square, this is a perfect square, and this is a perfect square, which is awesome. And so you might be tempted to jump right in and say, well, let's factor this as a difference of squares. However, there is a common factor of 4 here, and you should probably take that out first, okay? Make things a little bit easier. So if I take out that factor of 4, remember that 4 has been distributed to two terms here. So in order to figure out what's left over here, I have to divide that by 4, and I'm going to get 4y squared. Now, I'm still left with a difference of squares. It's just a little bit easier. The numbers are a little bit smaller here. So the square root of x squared is just going to be x minus the square root of 4y squared will be 2y. And then I'm going to multiply by the binomial conjugate x plus 2y. Let's take a look at another one. All right, 27m cubed minus 12m. Well, I mean, clearly I have two terms and I've got subtraction in between, but these are not differences. These are not perfect squares, I should say. But there is a common factor of m, clearly there, and there is a common factor of 3 to the two coefficients there. So I can factor out a 3m. And that's going to leave me with a 9m squared minus 4. Okay? When I divide that out, remember I'm going to divide both of those terms by 3m here. And then what I'm left with when I take that out is perfect square minus a perfect square. So this is a difference of squares. So it's going to be the square root minus the square root multiplied by the square root plus the square root. Okay, and so there we go. Difference of squares. 25 minus a squared. Okay. Now, I'll be honest with you, when I look at this, immediately my first reaction to this is to say that this isn't pretty. Okay? It is, however, a difference of squares. Please don't misunderstand me. This is going to be perfect square minus perfect square. So 5 minus a multiplied by 5 plus a. That's square root minus square root multiplied by square root plus square root. Okay, that works here. But I actually don't really like the way that works here. So what I want to do, just for the time being, is I'm going to make this adding negative a squared so that I can change the order that that's written in. I think this looks prettier to have the variable first. But I also don't like having the negative out front. We talked about that with the common factoring. So I'm going to factor out the negative, and when I do, that's going to change the signs on both of those. So this is going to be minus a squared minus 25. Now it's still a difference of squares, but the square root is now going to be a minus the square root of 25, which will be 5, and then a plus 5. I think this looks better than that. Okay, and I already know there's going to be a lot of people out there that would agree with me on that. That it looks better to lead in these expressions with the variable. Let's take a look at another one. 100x squared minus 81. Don't let the size of the numbers intimidate you. This is still perfect square minus perfect square. Square root of 100 is going to be 10. Square root of x squared is x. And the square root of 81 is just 9. So it's going to be 10x minus 9 multiplied by 10x plus 9. No big deal. And then finally, let's take a look at one more. 16x squared minus 64. Well, again, I'm noticing that this is a perfect square and this is a perfect square. But if I'm going to be asked to fully factor something, then I need to yank out what's common first. And it turns out both of these, okay, both of those have a factor of 16 in them. Okay? And the more you play with this, the easier it gets to see that sort of thing here. And if I divide this by 16, I'm just going to be left with the x squared. And if you divide 64 by 16, you'll be left with 4. And now what I'm left with is a very simple, straightforward difference of squares. So it'll be x minus 2 and then x plus 2. Okay, there we go. There's my difference of squares factoring.
And finally, we'll look at factoring by grouping.
Okay, so the final form of factoring that we're going to look at in this particular lesson here is factoring by grouping. Now, this occurs typically when you've got 4 terms. In fact, if you look at all the examples that we're going to do on this page here, they're all going to have 4 terms with them. So that's kind of your big clue that this is what you're going to do. Always take out a common factor first, if there's something that's common to all of those terms here. Then you're going to group the first 2 terms together and the last 2 terms together, and you're going to do that with parentheses. But what you're going to do when you do this is you're going to put an addition in between. Really important, this step right here. You are going to put an addition in between. And I'll show you an example of what happens when that kind of breaks down in just a moment here. But then what you do is you take out the common factor from the first two terms, and then you take out a common factor from the last two terms. And if this is working correctly, you should have a binomial factor that you can now take out of both of the terms. And then what you'll be left with is the factored form of that expression. Okay? Now, there's a great little point right here. If after you take out what's common, that first step here, if you don't have this binomial factor that's popping out that's the same, try rearranging the terms. Just rewrite the expression. You should be able to find a way that works. So let's just jump right in. Let's start factoring these things. So I've got four terms here. First thing I want to do is look for something that's common to all four terms, and I look at the x's there. There's x's in the first three, and the coefficients kind of in your last three, so there's nothing really common to all of those. So what I'm going to do is I'm going to group together with parentheses the first two terms. I'm going to group together with parentheses the last two terms. I'm going to put a big old plus sign in between. Now, what has been distributed to those two terms in this first set of parentheses? Well, just an x. And when I divide both of those terms by that x, I'm going to be left with x plus 4. In these two terms here, there's a common factor of 6. And when I divide both of those terms by that 6, this becomes x, and that becomes 4. Now, I can tell that I've done this correctly because what I've got now is in each of these terms is a common x plus 4, this binomial factor. Now, the last couple of times that showed up, I put a big old A on top of that. But to be honest with you, last time I did that, it almost, well, it obscured what was underneath and made it hard to read. So just know that that x plus 4 is common, that the x plus 4 has been distributed to two terms. So what did the x plus 4 get distributed to? Well, an x and a 6. Okay, this as one unit, this got multiplied by the x, then it got multiplied by the 6. So I just take it out, and that's what I get. Okay, let's take a look at the next one. Again, four terms. So the first thing I'm going to do is going to look for a common factor here, and I see 4x. Okay, there's another 4x here. Okay, well the 4 disappears as an option, and I've still got the x here, and there's no x there. So there's nothing common to all four terms here. Now, I'm going to group together these two terms with parentheses. Now, watch what happens here. If I now go subtract and then just don't even think about it, group together these last two terms here, just like this, in that step right there, I have done something incorrect. Because if you now try to drop the parentheses, I should just go back to the original expression here. But dropping the parentheses would mean that this negative gets distributed to both of those terms. Well, that's okay. That would make this negative 3xy. But that would actually make this a positive 15y. Well, that doesn't take me back up to this expression here, so I've done something wrong here. That's where this rule comes in. Put a plus sign in between. So what should have happened here was that negative sign, that negative 3x, that should have been moved inside the parentheses, and I put a plus sign in between. That is the way that should be handled. And now, what's common to both of those terms? Well, there's a factor of 4 in both of those, yeah. There's two x's here, one x there, so I can take that out. So what did I distribute the 4x across to get 4x squared plus 20x? X plus 5. If you divide both of those terms by 4x, you'll get x plus 5. What's common to both of these? Well, the negative 3 and the y. So if I take out a negative 3y, now if I divide both of those terms by negative 3y, I am going to get x plus 5. And so again, I know that I'm doing this right because I can see that common binomial factor right there. So now I can take that out, okay, and I will be left with x plus 5 multiplied by, well, what did I distribute the x plus 5 to? Well, 4x minus 3y. And there we go. That is the answer in factored form. Let's take a look at another one. Once again, first thing I want to look for, is there any common factors here? Well, x isn't common to all of those terms, and neither are any of the coefficients, because a lot of these have 2's in them, but this has got a 3 in there. Now there is a little bit of a shortcut that I can take here, but it kind of goes against the spirit of the question here. I mean, it is possible to add those two together in the middle here, and to reduce that, but that, like I said, that goes against the spirit of the question. You're going to see where that, having those two right there and separating them, might be useful in the future. So what we're going to do is we're going to group together with parentheses the first two terms and then the last two terms. There is a common 2x to both of those, and that's going to leave me with an x minus 4 when I factor that out. And then there's a common factor of 3 to these two terms. And when I factor that out, I will be left with an x minus 4 again. Nice common binomial factor. So that x minus 4 had been distributed to a 2x and a positive 3. And so there you go. In factored form, that is x minus 4 multiplied by 2x plus 3. Let's have a look at this one. A squared minus 4a plus 2a minus 1. And again, you'll notice that I could actually group together those two middle terms here, but again, that is not in keeping with the spirit of this problem here. So what I'm going to do is put parentheses around the first two, big plus sign in between, and then parentheses around the last two. What's common to both of those is going to be a 4, a factor of 4, and an a here. So 4a multiplied by, that's going to be 2a minus 1. Remember, 4a divided by that 4a is going to get you that 1 right there. Plus, well, there is nothing common to 2a minus 1. There's nothing shared there. But that's okay, because look, even though I didn't have anything to pull out here, I still end up with this common binomial factor. Well, that's kind of nice. So that 2a minus 1 was being distributed. What was it being distributed to? If you divide both those terms out here, in that first term I'm going to be left with a 4a. Well, if you divide this term by 2a minus 1, take a look at that. What do you get? Well, 2a minus 1 divided by 2a minus 1 is just going to be positive 1. And so there you go. That's what that looks like in factored form. Okay, let's take a look at this one. So here's another one where there's that negative sign in between. So, and again, I could group together those middle terms here, but I don't want to. What I want to do is put parentheses around those two, an addition sign, and I want to pull that negative in and make that negative 4x plus 6. What's common to 6x squared minus 9x? Well, there's definitely an x, but there's also a factor of 3. That's going to leave me with 2x minus 3. When I look at what's common here, I think back to what we talked about. One of the first things we mentioned was we don't like starting with a negative. So I'm going to take out a negative, and there's a common factor of 2 to both of those. So when you take out a negative 2, I'm going to be left with 2x minus 3. If you just focus on these little details that make these things prettier, easier to look at, by putting them in the right order, by taking out the negative, you do yourself a huge favor, because now look at that 2x minus 3 just presents itself. So I can factor out that common 2x minus 3 that I'm seeing to both terms. That has been distributed to a 3x. Okay, this was like 2x minus 3 multiplied by that 3x. And then that 2x minus 3 multiplied by that negative 2. Let's do one more. Okay, so in this last one, well, notice first of all that there is no common x to all those terms, but there is a common factor of 2, and I'm going to take advantage of that. I'm going to take out the 2. That will leave me with x cubed plus 2x squared minus 4x minus 8. And now what I'm going to do is I'm going to group together the first two of those two terms, put a plus sign there, and I'm going to move that negative in, negative 4x minus 8. Close brackets, close brackets. Now, what's common to those two terms? Well, there's a common x squared, so I can take that out. And I will be left with x plus 2. Okay, so that x squared was distributed to an x and a positive 2 here. Here, remember what we had said just moments ago, that I'm starting with a negative here. I don't want that, so I'm going to factor the negative out. And then I've got a common factor of 4 there, so I'll take out the negative 4, and that'll leave me with an x plus 2. Okay, so I've got this 2 out front, and then I've got this x plus 2 that was distributed. Now let's see what it was distributed to. It was distributed with an x squared, and then a negative 4. And there we go. Except that that's not done yet. Because the moment we pulled out that common stuff, notice what this is. That's a difference of squares. And so you are obliged to keep going with this. And I know this is a big one here. But now I need to rip this apart into its binomial conjugates. So x minus 2, so square root minus square root, multiplied by the square root plus the square root. So there's an awful lot going on in that problem. Kind of a nice nested layers of factoring going on there. It's a really good question. So I hope that helps clarify common factoring, difference of squares factoring, and factoring by grouping.